Now, let's focus on a key issue for any utility-scale photovoltaic plant: electrical substation failures. Although they don't always receive the same attention as photovoltaic panels or inverters, substations are the vital link between generation and the grid. When they fail, not only is production interrupted, but they also generate economic losses that can jeopardize the financial viability of the entire plant. The stability of energy evacuation depends on their proper operation, and any interruption can trigger contractual penalties, cost overruns for urgent repairs, and a direct loss of revenue from undischarged energy. This analysis is based on actual failures documented between 2019 and 2024. Using insurance reports, data from O&M companies, and laboratory studies, we identified recurring patterns, common failure mechanisms, and technical decisions that make the difference between stable operations and one with recurring risks. We included incidents in both desert and wetlands, considering environmental factors, design errors, and maintenance deficiencies that often accumulate over time to cause a critical failure. We'll see how seemingly small failures, such as loose contact, dielectric degradation, or poor insulation, can escalate in costs if not detected in time. Many of these failures are invisible to the human eye and require specific monitoring or inspections to be identified before they affect service continuity. But beyond listing causes, we seek to connect failures with their economic and operational consequences so that every maintenance or investment decision is better informed. Because when we understand why these systems fail and how to anticipate that failure with preventive actions, we protect not only production, but also long-term profitability. And this profitability is what allows a plant to plan for its future, ensure its returns, and maintain its competitiveness in an environment of increasingly tighter prices. Substations, although they represent a smaller percentage of incidents within a plant's total assets, have a high economic impact. They are often responsible for the greatest amount of downtime when a breakdown occurs and require more complex interventions, specialized personnel, and, in many cases, replacement components with long lead times. That's why this study is designed to help you make decisions with an integrated technical and financial view, focused on reducing risks, prioritizing critical investments, and maximizing the operational efficiency of your plants. Understanding the root causes of failures and their economic impact is not only useful for technicians, it's also a key tool for financial directors, investment managers, and insurers who want to avoid costly, unforeseen events and ensure the return on their renewable energy projects. To understand the operational and financial impact of breakdowns in a photovoltaic plant, we must start with the substation. It's not just about understanding the installed equipment, but also identifying which ones are critical, their probability of failure, and the consequences they can generate. It is in this infrastructure where any interruption can result in considerable losses. Transformers, whether conventional or GSU, allow voltage to be increased to evacuate energy to the grid. Their failure rate can reach 0.95% annually, and 28% of plants experience more than 120 hours of downtime per year due to equipment failures. This implies lost production, revenue, and higher maintenance costs. Circuit breakers are also key. With a failure rate of 2% per year, frequent problems such as gas leaks or mechanical failures can spread breakdowns and affect other assets, with significant economic and operational consequences. Electrical protections have a vital function, detecting faults and responding immediately. But a misconfiguration or functional failure can leave the plant defenseless or cause unnecessary shutdowns. Although their annual verification is mandatory, it is not always performed with the required precision. As for SCADA systems, they offer high availability, but their greatest weakness is cybersecurity. Attacks can alter data or commands, affecting both the plant's operations and reputation. Cooling is another critical aspect. If the system fails or does not adapt to the environment, the transformer's internal temperature increases, accelerating its degradation and reducing its lifespan. Insulators, exposed to aggressive environments, degrade over time, which can cause electrical shock or short circuits if not detected early. The lack of redundancy in many facilities means that a single failure can bring the entire plant to a standstill. Although there are regulations for annual inspections, compliance is uneven and often insufficient. In addition, there are cross-cutting risks such as dielectric oil degradation, dielectric oil leaks, calibration errors, or cyber attacks, which must be carefully managed. In short, although the frequency of failure varies depending on the component, any error can have a high cost. Therefore, it is key to prioritize resources for specialized maintenance, monitoring systems, and a preventive strategy that ensures the continuity and profitability of the operation. Now we'll focus on one of the most critical assets in any electrical substation, the transformer. Although its annual failure rate may seem low, when a breakdown occurs, the economic and operational impact is significant. It's the component that typically generates the longest and most costly downtimes, justifying priority technical and financial attention. Under normal conditions, conventional transformers have a failure rate of 0.53%, GSUs reach 0.95%, and in new photovoltaic plants, it can reach up to 50% in the first few years. This is due to factors such as lack of operating experience, adverse environmental conditions, and non-optimized technical configurations. 28% of plants experience more than 120 hours of downtime per year due to transformer failures. This downtime not only impacts operations, but also translates into real economic losses, especially in facilities subject to PPA contracts, where every hour of downtime means lower revenue. Average repair time is also key. Dielectric oil failures can take 48 hours to resolve, cooling failures around 24 hours, and problems in medium voltage switchgear up to 72 hours. Even overheating results in at least 36 hours of downtime. These cumulative times seriously compromise profitability. Among the most common causes are dielectric oil degradation, detectable through dissolved gas analysis, DGA, cooling system failures, which are particularly serious in hot climates, wear or leaks in medium voltage switchgear, which require periodic inspection, and progressive overheating, which can go unnoticed until it's too late. Therefore, anticipation is essential. A monitoring strategy that combines DGA, temperature sensors, visual inspections, and vibration analysis drastically reduces the risk of critical failures. It also enables more informed technical and economic decisions. From a financial perspective, replacing a transformer is a major capital decision. Its estimated lifespan of 40 to 50 years can only be achieved with proper predictive maintenance. This type of maintenance not only extends the equipment's lifespan, but also protects the initial investment and reduces the total cost of ownership. In short, the transformer represents the substation's most delicate bottleneck. Even if it fails rarely, its consequences are very costly. And the only sustainable solution is predictive management based on data, advanced technology, and strategic planning. High and medium voltage circuit breakers are key components in a substation, and their failure can lead to unwanted tripping, loss of protection, or service interruptions. Although they appear to be passive elements, their impact is critical both on technical operations and economic results, as a single failure can shut down the plant and lead to contractual penalties or losses due to undelivered energy. The annual failure rate for high-voltage circuit breakers is around 2%. This may seem low, but in plants without redundancy or in GIS systems, this percentage represents a high risk. Among the most common technologies, SF6 gas circuit breakers stand out due to their insulation efficiency, followed by vacuum circuit breakers, which require less maintenance, and the less common air blast circuit breakers. Among the most significant faults, SF6 leaks are particularly worrisome. Reducing gas pressure compromises insulation and increases the risk of arc flash. Furthermore, SF6 is a greenhouse gas, which also introduces an environmental and regulatory dimension. Another common fault is contact wear, the result of repeated operations that generate overheating and increased electrical resistance. Added to this are failures in actuation systems, which can prevent the breaker from opening or closing, leaving the system unprotected in the event of a fault. According to statistics, 35% of faults cause unwanted tripping, 28% involve loss of protection, 22% cause overheating, and 15% correspond to other problems. These data underscore the need to detect breaker degradation early by monitoring parameters such as gas pressure, contact temperature, current, and operating times. Implementing specialized condition-based maintenance, including functional testing, gas analysis, and protection calibration, not only prevents failures, but also extends the equipment's lifespan. A breaker failure is not a minor incident. It can trigger a chain of consequences. Therefore, anticipating this with appropriate sensors and robust maintenance protocols is not only a technical measure, but also a smart financial strategy in an increasingly demanding sector.